afternoon, fancy meet computers. Well, got one person out there in television land. How do you do? Is there a midterm or something? I don't use a TV to watch your lectures. Too cheap. It's kind of funny that, like, most smartphones have higher resolution than most televisions, you know? And the smartphones are normally more expensive as well. Well, maybe not. If you get a cheap smartphone, it's pretty inexpensive. Let's see. Oh my goodness. 9 people, but I only see 3. That's crazy. Cool. For project 2, questions 8 and 9, were we supposed to put evaluation in our functions or just have the functions type check? Or an expensive TV, yeah. You were just type check, not evaluate. You can evaluate them to find out if you did them correctly. That would be one way to do that. But, you know, most of them were pretty easy, so hopefully they weren't, you know, too bad. But yeah, no, it was just, like, they weren't supposed to evaluate, you know, like, they are all functions, and they do evaluate values when you apply the semantics to them. But the point was just to write the terms of the calculus that represent those operations. So, here we are. Well, here we are again. It's always such a pleasure. Remember when you tried to kill me twice? Oh, how we laughed and laughed, except I wasn't laughing. Given the circumstances, I've been shockingly kind. I don't know, are you folks, like, too old now for, or too young for Portal? Is Portal like an old man thing these days? I wonder. Anyway. Nope. Okay, good. I wouldn't say Portal is an old person thing. Awesome. I'm not old yet. All right. Wow, look at Mark flexing in the chat. One might say Portal is. I'm waiting for the punchline. Still alive. Ah! Very good. All right. So, we should get started. I think we've had our requisite 3 to 4 minutes of fluff before the lecture itself gets started. So, this is kind of an exciting lecture for me. This topic is kind of an exciting topic for me because we're getting into stuff that's like we've been in theory land for so long. I don't know, but maybe there was space to improve. Very good. Yes. Imerpov. Yes. Imerpove. So, we're going to actually start talking about, like, some real constructs that are more complicated than Booleans. So, this is exciting. So, first, however, let's talk about church versus Curry style. And I'm not talking church versus Curry style of, like, jiu-jitsu. So, although it's kind of like, no, it's not at all like jiu-jitsu. So, Curry style. Our general approach to language design in this class so far has been, number one, start with some terms representing desired behaviors, that is to say, syntax. We then formalize these behaviors using evaluation rules, i.e. semantics. And finally, we apply a typing system to reject undesired behaviors. That's typing. This is often called Curry-style language definition because semantics are being given priority over typing. I.e., we could remove the typing and still have a functional system. If you guys don't mind, I think I'm just going to close the door. Mom's just trying to get the kid down for a nap. Ugh. So, it's kind of funny, like, once you're a parent, you do, like, it is true what they say, that, like, there is a communication, there's, like, a language of baby cries, you know? That's his, I'm really tired, and I would like to sleep, but I don't know how, so we have to help him. Might also be hungry. Anyway, so the point of Curry style is that the terms of the language and the semantics of the language are primary considerations, and the typing is like a secondary system that we layer on top of it in order to, you know, be able to reason about the correctness of the thing that we've put together, assuming it's been constructed correctly with respect to the syntax, right? So it's like your first layer of rejecting bad programs is it doesn't even conform to the language's grammar. Your second layer of throwing away programs is it doesn't conform to our typing specifications. So, effectively, you know, as we were discussing with Erasure, fundamentally all of the typing information that we're producing is going to be thrown away anyway by the compiler to produce the object code. So, we have been very, very... define the baby lang in Curry style. Oh my god. Now that is not a context-free grammar. So the idea is, with Curry style, that you can, like, because the typing apparatus is separate and distinct, it's easy to just peel it off at the end, and then you're left with something that still makes sense. That is strongly juxtaposed with church style. So, Curry, of course, being named after our old friend Haskell Curry, whose name is given to the Haskell programming language, and whose second name is, his family name is given to Currying, which is, apparently he didn't invent, but people named it after him anyway. That's how famous he is. And then Alonzo Church. So, here's a different approach entirely. Start with some terms representing the desired behavior. So, we start with the syntax, same starting point. Number two, identify the well-typed terms using typing rules. So, typing is secondary, and then give semantics only to the well-typed terms. So, whereas Curry style is syntax, semantics, typing, in Church style, it's syntax, typing, semantics. So, under Church style language design, typing is given the top priority, in the same way that the evaluation semantics are given top priority during... Alright, thank you. Gonna close that. One time during a lecture, I got like a pop-up message from a TA that was just like a skull and crossbones, and I was like, should remember to close that. Anyway, so under Church-style language design, typing is given top priority. Questions like, how does an ill-typed term behave, don't occur because no ill-typed term can even be evaluated. Can't even evaluate them. So, like, this is a very different way of thinking about it, right? But, further to that, historically speaking, explicitly typed languages have normally been presented in the Church style, and implicitly typed languages have normally been presented Curry style. Oh boy, Nick, you're not going to like what... Oh, okay. After lecture. But I think I can guess. I can guess what that's about. A bunch of the first years are in a flap because they all cheated on the test and we caught them. That's what I imagine the flap is about. But anyway. So, yeah, that particular gigantic log of shit is continuing to plow its way through the fan at this as we speak. So, anyway, so because historically speaking, explicitly typed languages are done Church style and implicitly typed languages are done Curry style, people often confuse explicit typing with Church style and implicit typing with Curry style. Oh, okay. Well, that's fine. So Church style is sometimes confused for it. So sometimes, like if you read an older textbook, or if you read a textbook that's written by a person that doesn't necessarily understand this stuff very well, but it's like a survey textbook of programming languages, which, believe me, I've seen some pretty bad textbooks on programming languages. That's why I love the Pierce book, is because it's like, oh, this is a good textbook. But anyway, so sometimes they'll confuse the two, but it's important to understand where Church and where Curry come from. So there we go. All right. Any questions about that? If not, we will move along. This is a very important slide to me. So, only now, in the first week of November, can we begin to have an intelligent conversation about the design of programming languages. That's right, folks, we're going to start mixing in real-world constructs now. Well, you know. What do I mean by implicitly typed versus explicitly typed? Time to shit on Python. Yes, it's Python shitting time, yet once again. No, it's, so what do I mean by explicit versus implicit? So, you know how when we did typing rules for Lambda abstractions, right? When we did typing rules for Lambda abstractions, we included the typing tag on the variable being abstracted, right? That is a form of explicit typing. If you know, essentially, we've started off studying explicitly typed languages because we're using typing tags, right? We've started off talking about explicitly typed languages because implicitly typed languages require type reconstruction. Type reconstruction is chapter 22 of the book. And since we're only on chapter 11 of the book, I don't think we'll be able to make it to chapter 22 before we manage to finish the course. Yeah. Chapter 22, type reconstruction. That doesn't really work, but anyway. Type reconstruction. So the general idea of type reconstruction is that if you loosen things up a little bit with polymorphism, then you can actually use the typing rules themselves to be able to derive what the types of everything is supposed to be. Basically, you just recurse back to literals and draw the literal typing rules forward, and you should be able to figure out what most things are typed, at least within a couple of types. So, in theory, it's possible to write a programming language without any type annotations at all, such as our beloved Snake language. Speaking Parseltongue. So, I have, roundly abused Python in this course so far, however, for explicitly the fact that typing annotations are useful. And to not use them is a problem because it makes the whole purpose of the typing system is to make sure that the program works correctly. If you don't have a typing system that is explicit, then the programmer doesn't see anything, which means the typing system isn't working, because it's partly for the benefit of the programmer. But, anyway. So, yeah. Explicit. If you want to think implicit typing, think Python. If you want to think explicit typing, think Haskell. Although, pretty much every language does some degree of type reconstruction these days. But, Haskell, because it's so strongly statically typed, it's one of the best ones, JS was 2 plus 2 minus 2 equals 20. Yeah. 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 Cool. I don't know enough about JavaScript to shit on it, to be honest with you. Yeah. Yeah. So let's talk about real stuff now. So, up to now, we have only used Booleans and natural numbers. But you may have noticed from other programming languages, or any programming language, JS attempts type conversion over errors. Wow. That's why you only use TypeScript. Yeah, it sounds like JavaScript is terrible. I've heard the one Java is to JavaScript as car is to carpet, but yikes. So with atomic types, that's being said, my first programming language ever was ActionScript, which was a JavaScript ripoff that they'd embedded in the Flash player, because I did Flash programming as my first thing of real programming. But anyway, so every programming language provides a set of atomic types, which normally include Booleans, integers, unsigned integers, real numbers, characters, strings, etc. Your primitive data types. These are sometimes known as primitives. The reason I'm calling them atomic is A, because it's it works with the meme. Actually, the meme was selected because we called them atomic, not in reverse. And also, they're indivisible, right? It's how do you divide an integer up further? You can't. Strings, it's yes, they're divisible into characters. However, it's useful to be able to deal with a string as if it were a primitive, so we often, in most languages, we have the facility to deal with strings as if they're primitives, right? But anyway, these are sometimes known as primitives. These are normally accompanied by a set of primitive operations, such as plus, minus, multiplication, division, equality, logical and, logical or, etc., 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 your standard suite of arithmetic operations. We have discussed Booleans and naturals at length thus far. The rest of these operators and types can be added to our language semantics in a similar way. So this sentence hand waves away about as much work as we've done in the course so far to establish the rest of the data types in any of our languages. This is what's happening right now. We are hand waving this entire course, like repeating this course over again to talk about, integers and floating points and all the rest of it. This is the hand wave. See the hand wave? Hand wave. For the rest of this course, we will occasionally bring in the rest of these data types in order to make our examples more interesting. Aren't these primitive operands and their functionality the operations? These symbols are not the actual algorithm that goes on behind the scenes. Yeah, that's the point, right? It's kind of funny, this coming from a guy who just wasted the last 2 of your months, reteaching you what, plus means. But we don't actually need to tell you what plus means. We're going to assume you know what plus means from now on. The reason that we, did all of this work over the last 2 months is to establish, how we can rigorously talk about these topics, right? It was the methodologies that were important, not the particular, it wasn't the fact that you now know how plus works in lambda calculus. That wasn't the important bit, right? The important bit was you now know the process for getting something to work in lambda calculus. And you know what lambda calculus is, what it's capable of, what it's not capable of, right? That's the point. But anyway, so, abstracting the types. In order to reason with our ever-expanding language definitions, it will be useful to abstract away the details of these types and their operations. So, we just remembered them, now let's forget them again. Let's suppose that our language comes with a set A of uninterpreted or unknown base types. Open store to lecture. Hi, Joe. I just explained to the class how the last 2 months have been useless. Or how they've not been useless in context of, one sentence on the previous slide. So we have some set of base types, right? Or atomic types. Base type, atomic type are synonyms. Maybe this particular language, doesn't have a type for nat. Maybe it just has, integers, booleans, reals, and characters. That's fine. We don't actually have to care about the details, right? We can just say, it has some set of base types. Our function, this is mainly so that we can get out of the problem of pure lambda calculus being degenerate because it doesn't have any base types, right? So if we take pure lambda calculus, throw in these base types, we no longer have a degenerate type system. So, in addition to this, let's just assume that we don't have any primitive operations to worry about either. Again, we're going to hand wave that away. We can accomplish this by including the elements of A in the set of types T for our language. This is pretty simple. So, our set of types is just going to have A tacked on, and we're not going to worry about operations. Note that this extends simply typed pure lambda calculus. For these sets of atomic types, we will use the names A, B, and C as the names of these types. So, we'll do iterations on A in the same way that we usually do, T, S, STU, or, letters in the vicinity of T. Oh, yes, there we go. Sorry. We will also use A to mean a metavariable, which ranges over the atomic types. These two will always be distinguishable from context. So, it doesn't seem very useful to have a variable for a bunch of types we haven't specified, especially when they don't even do anything, because they have no operations. Actually, this is not so very different from the way that we've been doing things so far. What it allows us to do is it allows us to assign types to variables in Lambda abstractions and then reason about them, right? So we are allowed to include elements of A as our types, right? So this is going to be to some degree useful. It's like, you remember like how like a couple of weeks ago it was like we were introducing functions from bool to bool, and like bool to bool to bool to bool to bool, you know? Now we don't have to say that. We could say A to B to A to C to D, right? And we just don't care what A, B, C, and D are. So, for example, lambda x typed A, x is typed A yields A, and that's an identity function on some type A. And then if we have lambda f, where f has type A yields A, lambda x of type A, f, fx, this takes in a function and applies it twice to x. So there we go. Any questions? Good. This should be pretty easy, right? If you're still coming to class after all this time, this is probably fine. Do we really only have 6 people in the class? No, that can't be right. We have 14. Thank you. Thank you, YouTube, for accurately, telling me how many people are in my class. Not. See, that was sarcasm. So, now things are getting... I'm glad to see Gamma is gone. Yeah. Enjoy that while it lasts. So far, our languages have consisted entirely of stateless expression simplifications, which is okay insofar as it goes, but we have not really progressed much beyond doing basic calculator operations, Like the type of operations that we are currently doing, you could foresee, like you could see, like in a parallel universe, somebody had a calculator where you could do lambda expressions, and like that's what we've been doing so far. What we want to work towards... gamma, llama. Yes. What we really want to work towards is the type of constructs that are held in real-world languages. Things like your Python, or your C, or your JavaScript, or your Java. It will be necessary to find formal mathematical expression for the concepts of assignment and sequencing. In essence, we need to move from just talking about expressions to also talking about statements. Remember the difference between an expression and a statement? So, consider a simple imperative assignment operation, like in a language such as C. Right? What does assignment return? What type would it have? True to form, we will answer these questions as laboriously as possible. I'm actually interested to hear what you have to say, though. What do you think, like, if I opened up, let's talk about Python, because everybody knows Python, right? If I did in Python, I said x equals 5, and then I said execute, what is the return value of the expression x equals 5? And what type would it have? What do you think? I open the floor. Possibly a long. I feel like assignment returns a memory address of the variable created. Possibly a long integer. Any other ideas? That's a good guess. Python would make it an instance of the int class because it's dumb. Like not even a value. That's getting closer. Or nothing. Right, but what is nothing? So it's kind of a trick question. Essentially, what we need is we need something like a void type. Right? Like, even C has a void type, right? Yeah, it's not quite the same thing as a null pointer. We're gonna formalize this idea though, right? Yeah, it's like we're gonna call it something different, but it's essentially a void. Yeah, void, none. These are, basically the idea, right? So, in general, we don't think of assignment statements as directly returning anything. More on assignment next week, folks. So for those of you who have been following along in the textbook with the course, which I know there are a couple of you, which if you are, kudos. We're going to do up to 11.5 in this lecture. Then we're going to skip the rest of chapter 11 and jump right into chapter 13, which actually talks about how you do referencing. What the textbook means when it says referencing is something like formalizing the idea of storing things in memory. So, there we go. So, the interesting part of an assignment statement is the effect that it has on memory, right? In other words, we perform assignment specifically so that we get a particular side effect. Side effects are like a pretty broad category of different types of things. Haskell is famous for not having side effects, quote unquote, not having side effects. It does, but it hides any side effects from you, essentially. Like, it's not like Haskell doesn't use memory, But that's the claim with Haskell, is that when you run a function, none of the operations have side effects in the specific sense that we're using it here. So side effects include things like memory manipulation, displaying data using standard output, taking keyboard inputs, and many other useful things that computers do. So, like, when a computer interacts with any of its other various systems, like the operating system or, any of the buffers or anything, even like displaying something to the screen is considered a side effect, right? So we're not interested in the return value, so to speak, of the assignment operation itself. The only reason we perform the assignment operation is to have an effect to have one of these side effects. So, assuming that our goal for type theory as a science is for all correct behavior to be well typed, how would we go about giving a type to such operations? Essentially, we want something like a blank or an empty type. We shall design such a type, unit. In the last section, the atomic types were uninterpreted. That is, we didn't care about the internal details or evaluation mechanisms. We didn't we added the type, but we didn't add any terms. We didn't add any rules of operation. We didn't add any operations or anything. They were just uninterpreted. But unit will be interpreted. It will be interpreted, but very simple. Semantically speaking, we want unit to behave roughly like the void type in languages like C and Java. And possibly the none type, like in, well, I don't think none type is actually a good analogy in Python, because none has a literal. I'm not sure. Question to the crowd: does void in C have a literal associated with it? I don't think it does, but I could be wrong. Like when you return from a void function, you just leave the return without anything provided, right? Like you don't, like in Python, if you want to return a void type, you return none, right? And that's none type. But in C, it's just, you just type return, right? I don't know, maybe somebody knows more than I do. But yeah, so that's unit. Here are our unit semantics. In the above, these semantics extend simply typed pure lambda calculus. You can return a null pointer, I think. I don't know. I don't know that much about how it works like at that level. Anyway, so we've got a new term, right? Notice this is unit with a lowercase u. It's also a value. It's also in normal form. We have no evaluation rules for it. And we are adding one new type, unit. And we have one new typing rule that the unit literal has type unit. So, don't worry about this guy. We're going to be talking about him shortly. This is the sequencing operator. Return void thing. Oh, cast it as void. Interesting. So anyway, in the above semantics, we introduce not only a new type unit, but a term unit as well. We also define unit as a value. We have no given evaluation rules to unit, so it is a normal form. And the new typing unit, tunit, sets the term unit as having type unit. In the absence of further additions, we can easily derive inversion lemmas and canonical forms from this description, right? I'm not going to bother deriving canonical form and inversion lemma from this. I will leave that as an exercise to the reader. So, let's talk about sequencing. Here's a question, though. Does anybody have a high enough IQ to understand this meme? You would have had to have read the book, I think. Also, are there any questions about unit type? Hopefully not. It's relatively simple, right? All hail the obelisk. I will explain the meme. So, in the movie and the book 2001: A Space Odyssey, you have this sort of group of apes who are the things that eventually evolve into human beings, right? And this alien artifact comes down, right? And, like, in the books, it's kind of like modifies them slightly, you know? They interact with it, that modifies them and puts them on the path to becoming intelligent creatures that are capable of space flight. So, my meme here is that the idea that you can sequence operations is to programmers what the obelisk is to the apes in 2001: A Space Odyssey. It is the civilizing force. So, and it's not called the obelisk, it's called the monolith. Thank you. The monolith. So, if you haven't watched that movie, then you're in dereliction of your duty as a nerd. Anyway, so, sequencing. In languages with side effects, it is often useful to evaluate 2 or more expressions in sequence. In fact, one might say it's gosh darned essential. In programming languages that aren't snake language, this is achieved with a semicolon. Semicolon does have the semicolon operator, though. Or, Python does have the semicolon operator. Yes, but nobody uses it. Very few people actually use the sequencing operator in Python for sequencing, because you just put everything on a new line, right? In Python, new line is implicitly your sequencing operator, but, you know, whatever. It's like, Python doesn't have semicolons. It's like, well, it does. It's like, well, nobody uses them. So, for this course, we will consider T1 semicolon T2 to be a sequencing operator. Semantically, we want semicolon to execute T1, throw away its trivial result, and then go on to execute T2. We assume that T1 has some kind of useful side effect so that it's not completely pointless. In terms of typing, we expect T1 to be of the unit type, and we make no constraints on what T2 is. So, in general, there are 2 approaches for formalizing the semicolon operator. Number 1, we can define a new term for it, complete with typing and evaluation rules. This finally feels less like math. Right? This is what I was saying! I want to pick up the camera and shake it. Except I taped it to the wall. Because I had to get this funky, like, laptop tray for my laptop. Because, like, I've been I'm not going to show it to you because it's all wired in. But I had to get, like, one of those elevated laptop trays so that I could fit an ergonomic keyboard underneath my laptop and, like, be looking at the correct position, because I just about exploded my wrists this semester because of all the typing I've been doing. But, so my camera is now taped to the wall, so I can't just pick it up and shake it. But, well, maybe I can. Yeah. There we go. That's close enough. Yes, this is starting to no longer feel like a math course. Thank you. So anyway, there are 2 approaches to formalizing semicolon. We define a new term for it, complete with typing and evaluation rules, or we can define it as a derived form. That is, we define it in using our existing terms, requiring no new evaluation or typing rules. So, please don't, it's the audio source. Oh, whoops. Yeah, I forgot that that's the audio source. I'm sorry. I'm sorry, everyone. I got carried away. I'll try not to let it happen again, but I make no promises. So, when I'm talking about derived form, like, derived forms are actually, like, one of the very important things to take away from this lecture. Like, when I'm talking about external versus internal languages, external languages contain derived forms, internal languages do not. So it's important that you understand the concept of a derived form. There we go. No, it's okay. It was funny. Okay. As long as it was funny. If I'm doing it for the memes, then I shall continue to do it for the memes. But, so, with the derived form, What I mean when I'm saying derived form is roughly the same thing we did when we defined, like, for example, true and false and plus and the church numerals and all of that stuff in lambda calculus before we enriched it, right? Remember all that work that we did? And then we were like, and now we get to enrich the calculus, and all of our work is for nothing. So the reason that we were doing that is because we were setting you guys up conceptually for the idea of derived forms. The derived forms do essentially the same thing, right? You can define them in terms of the underlying calculus, but as programmers, we can have more convenient abstractions to work with. So, a wild new term approaches. So let's just define sequencing the way that we would define it classically in this course, and then we can talk about the derived form. This will give us a good idea of how the semantics work. So, defining sequencing as a separate term, we would start with the following grammar. We add the term semicolon, term. Good. To this, we would add the following evaluation rules. Number 1, a congruence rule. If T1 can be evaluated, we can evaluate it. Run. Okay. Don't know what that means. So, our second evaluation rule, if T1 is unit, that is the unit literal, so unit sequenced with anything yields anything. So once we have evaluated our T1 down to the level of it just being the unit literal, we have accomplished that. That's like saying this calculation is complete and then moving on to the next one. And we move on to the next one by throwing away T1. We no longer need it. We have calculated it. So, this is good. And of course, we need a typing rule because we always need a typing rule. So the gammas are back. Sorry, Mark. So if T1 can be found if T1 has type unit and T2 has type 2, then the type of T1 sequenced with T2 is just type 2. Essentially, we throw away T1. Again, we are assuming that T1 does something useful other than its return result. Oh, I get it. I get it. I love this class. Y'all have a sense of humor. It's much more fun when people have a sense of humor. So now that we have an idea of, like, so you hope, you can see, I hope, how this works, right? So imagine you had, like, a C program that was composed of, like, you know, let's just forget about if statements and loops for a moment and, like, just focus on, like, one log series of executions, right? Each statement there, when it hits, like basically what we're trying to do is we're trying to construct a mathematical system that does the same thing that the computer and the compiler does, right? So in our mathematical system, we can now evaluate, keep the side effect, throw away the result, and now we move on to the next one, right? Ordinarily, we will omit parentheses if we have to sequence more than one operation, because, you know, that would just, like, to the extent that lambda calculus is parenthesis hell, if you had to do precedence ordering on all of your sequenced operations, that's just... No, thank you. I guess the thing I'm supposed to say to Joe's a joke is, what is it that the Pokemon game says? It's, couldn't get away? I think it's couldn't get away. I've been playing Dragon Quest lately, and the can't escape message there is like, but the monster blocked your escape. So, Dragon Quest is very verbose. Well, I guess we'll do the derived form next time. You couldn't get away. There we go. Thank you. So we'll do the derived form next time in class, but are there any questions about this so far? Conceptually speaking, this is supposed to be a lighter week, conceptually speaking, right? Hold on to your butts, though, because, again, I'm not sure that this is going to come through on the slides, or on the... Oh my god. The equations are going to get big again once we start talking about data structures. So my plan... I actually, at this point, I can sort of formulate a plan for the rest of the course, because I think we've got, 4 weeks left, right? So, next week we'll do sequencing, which is chapter 13. Well, references, but that works its way into sequencing very well, right? Yes, you may ask an assignment 7 question. Absolutely. So chapter 13... then we'll hop back into chapter 11 and do the data structure stuff that I'm skipping over, right? Chapter 12 is I think that's an implementation chapter again, like an ML implementation chapter, which I generally skip and make them into projects instead. Normalization, maybe. I think maybe we'll skip I don't know. Short, I don't know. I'll see if I can squeeze normalization in. And then, after we've done safety, we'll do exceptions. And then, I was planning for, I think for the last week of lecture, I'll do, a survey of the advanced topics in the textbook. So, we'll do a rough intro to subtyping and polymorphic types and type reconstruction, just to give you a flavor for how that type of junk works without really getting heavily into the math, But, so, the question is, can you give us all the answers so that we don't want to die? No. So, for question 1, re-omega function. Do you have any advice where to start with making our decision? I don't think looking at the definition of well-typed has really helped me so far. So, I don't want to say too much about question 1 because it's kind of it's kind of a more open-ended question intentionally. I'm interested that people should come to their own opinion about it, if that makes sense. So, you don't have to... This is not a question where I'm looking for a correct response. I'm looking for you making a statement and backing that up with facts. And if you miss some of the facts about it, then, that's not going to be a huge... that's not going to be a huge penalty in this particular question. But yeah. So, yeah, it's I don't want to say anything. Because it's if I say X, then you're gonna, you're gonna know what I'm thinking, and I want to hear what you think. Yeah. Yeah, no, yeah, okay. Can you state both arguments and just not decide? Yeah. Agnosticism is, in this case, I think, a valid result. But yeah, I kind of like that this question has, started a discussion. That was kind of the intention. Yep. The rest of assignment 7 should be relatively straightforward, yeah? I hope that I made it to be relatively straightforward. Cool. So I brought the book, by which I mean I left it by my computer so that I could reach behind and grab it, because I'm in my house, so I have all of my stuff here, but, you know. The book I was talking about yesterday that I'm reading, which is The Enchiridion, and selections from the Discourses of Epictetus, which is Stoic philosophy. Question 1K, keeping me awake at night. Well, don't let any math problem keep you awake at night. Yeah. If you don't mind, I kind of just want to, you know, like read one or two of these to you, because it's really cool. It's like classical wisdom writing, so it's like a series of small, sort of pithy sayings. It's like Gnostic wisdom, but it's kind of a hobby of mine, reading wisdom literature from various cultures around the world. But yeah, so it's called the Enchiridion, which, you know, if all of you kids who were raised on Adventure Time thought that the Enchiridion was just a thing in a cartoon show, well then there you go. Proved you wrong. Ha. So, let me see if I can find a good one. Here we go. So this is number 5 of the Enchiridion. And I should say before I read this that this is like translated from ancient Greek. So the sentence structure is like very non-standard and barely English, but you know, we can get through it. Men are disturbed not by the things which happen, but by the opinions about things. For example, death is nothing terrible, for if it were, it would have seemed so to Socrates. For the opinion about death that is terrible is the terrible thing. When, then, we are impeded or disturbed or grieved, let us never blame others but ourselves, that is, our opinions. It is the act of an ill-instructed man to blame others for his own bad condition. It is the act of one who has begun to be instructed to lay blame on himself, and one whose instruction is completed, neither to blame another nor himself. Boom. I got a comment on the last video. Came for the math, stayed for the Stoic philosophy, so, you know, I have to keep that going now. Bloop. Well, anyway, if there's nothing further, then I'm going to log off here. So basically, ignore everyone else's opinions. Yes. Possibly even ignore your own opinion. Yeah, no, actually, another part in here, one of the ones I liked was, reputation is the chattering of madmen. It's basically like, if you find something disturbing, know that it is you that is disturbed by it. It is not disturbing in and of itself, right? Like, you know, like they like the example of death because of its finality, right? It's like if you examine the concept of death, the only reason that you're terrified by death, if you're terrified by it, is because, essentially because of your mental weakness. If you had like mental strength, like, you know, it wouldn't bother you. Like, there are people that it doesn't bother, right? And it's because, like, people like, and like there's an element of that that's really true because it's like, when you allow something to terrify you, you're allowing that thing to have power over you, right? So when you're afraid of death, you're allowing death to have power over you, right? And like, generally the Stoic approach is, you should only worry about the things that are in your control, and death is not in your control, so there's no point in worrying about it. Anyway, I'm gonna log off here. If you guys enjoyed that, we can make that a running theme. But take her easy, folks, and you know, give 3DB3 my regards. It's a lot of classical conditioning stuff. Well, classical in, like, the ancient Greek sense.